Substitute this one here again, you will end up to very nice equation m, let me write it in blue, m alpha beta comma beta alpha plus q or minus q, doesn't matter, depend on the direction that you will have. Minus q, for example, minus q equal to 0. You will substitute here, this will end up to d, as we said here, d times nabla 4 u3 equal to q, plus or minus, it doesn't matter. So you will end up to the mathematical equation u3, or the biharmonic operator applied on the deflection equal to q over d, and this is the equation for the simplest theory. It is very easy, and you can apply finite difference on it straightforward instead of solution of two differential equation like that. Instead of solution of two differential equation like that. So what Kirchhoff did actually again is two approximations. The first approximation is to set up the shear strain to 0, set up the shear strain to 0, and it end up to that the rotation is the derivative of the deflection. And he differentiated the second equilibrium equation. When we differentiate, as I said, we lose information, and we end up to combine the two equilibrium equation together to this very simple equation. By the time, at the beginning of the 20th century, this equation is very easy and you can solve it direct. Still, I didn't talk about the generalized Navier equation, which is the equilibrium equation in terms of the generalized displacement, because we have deflection and rotation now. We need to set it up in front of us in order to be able to form the differential, the fundamental solution, or we can get the kernels of the fundamental solution. Up to now, I finished what I want to talk about in this lecture. I hope that you try to grasp what is going on in plate bending basic equation. Maybe after that, I will continue to derive the fundamental solution for elasticity. Then I will derive the fundamental solution for plates. And I'm going to derive the integral equation for plates. And then we will be able to compute the integrals, whether they are regular integrals or whether they are singular integrals. It's very important to talk about the C matrix or the jump term, because when we go to formulate the hypersingular equation or the traction equation in order to model the two crack sides with displacement equation and the hypersingular equation, we'll do the same, but in advanced level. Up to now, if we have any problem or any questions, I'm ready for this.
Okay. Thank you, Professor Youssef Rashed. Thank you for your presentation. You have introduced two different plant series, the generally plant series and the classical thin plant series.
Yes.
And when should we use the generally plant series, and when should we use another one?
Okay. This is good question. Good question. Actually, if you want, we have the general plate theory, and the simplate theory. This is the classical.
Yeah.
Actually, this is valid for everything. This is valid for everything. In boundary elements, this is valid for everything. This one will create a lot of problems. Okay? Will create a lot of problems. Okay? I will show you now. But if you go, for example, in finite element, when you use this one, you will end up to shear locking. Okay? So you have to move to thin plate theory. When you have the plate is very thin, sometimes the elements are frozen. Okay, because of that they move to thin plate theory. So I hear that there are finite elements without shear locking, but I'm not expert in finite elements, and I prefer to keep myself in boundaries. The only thing I like to penetrate in finite elements when we have fundamental solution based on finite elements, the one introduced by Professor Zhuojia. Okay, and he's really great guy. He's really great guy. We have to admit that this guy have done a lot of contribution to boundary elements, to be honest. Okay, but generally in boundary elements is much better to use the general plate theory or the thick plate theory. Why I don't like using boundary elements here? Look back to this equation. If you look back to this equation, when you carry out the weighted residual statement or it, so to swap between these two functions, for example here, if you integrate over the domain U4, U3 times the fundamental solution, so what you need 4 times integration by parts to end up to single integral equation. This single integral equation, you have the deflection, you have the slope, you have the moment, you have the shear. And all the boundary condition, always you have 2 values. So you need another integral equation. So what we do is to differentiate the integral equation we obtained. So if this differential equation of order ln r and 1 over r, so the new one will be of order 1 over r and 1 over r squared. So practically in simplate theory, you use hypersingular equation to solve this equation. So you will end up with a lot of complications here. A lot of complications. You simplify mathematics, but you will end up with a lot of troubles in singularity. In fracture, you will need thick plate theory. You will need, because you ignore the shear strain. And one of the modes for the fracture, you will have the tearing mode. In the tearing mode, you have is governed by shear, and you ignore the shear strain. You ignore the shear strain, not the shear stresses. So it's much better to keep ourselves here. These are very promising, and I did a lot of work in this area. I did a lot of work, and actually our software is called the PLPAK. Look at it, PLPAK.com. If you look at this software, it's totally developed to solve. We solve it practical buildings, practical foundations, solid structure interaction, piles, all kind of foundation we have, dynamics, everything. It is very, very, very stable theory. Okay.
Okay, thank you, Professor Youssef. And I think maybe the same planned series is solved to this problem, and we can use the same planned series. Isn't just have the small value we should consider, and this is maybe calculated more faster to the general parent series.
To general, no, I can't hear. Can you say it again? It is easier equation. When you teach, for example, for undergraduate, it is easy for a student to look at nabla 4 W equal to something. Nabla 4 U3, W is the deflection. Okay, but
yes, okay. I will to see this website.
Yes.
And to know.
Yes, if we expanded this one, if we expanded these equations in terms of displacement, we'll have matrix operator. We'll have matrix operator. When a student sees this, and engineering student, when they see this, will say, oh, this is a lot of mathematics. But practically, if you go for programming or something like that, you will find these mathematics are very elegant and very, very nice to deal with. Okay? Still,
okay, thank you. I will to see this website.
Okay.
And to learn it.
Sure. Thank you. Okay. Any more questions?
Yeah, so any more question? So
no more.
Yeah, if no, maybe we'll close today's.
Okay, so time to say goodbye now.
Yeah, thanks for the teaching. I think
thank you for listening to me. Still, I have to remind you, I am waiting for any questions throughout the week. On WeChat, you can send it to me direct, and I will reply direct. Okay?
Thank you,
thank you everybody, and bye now.
Yeah.
Bye.
Okay,
so
thank you. Bye.
Bye.